Welcome. In this session on linear data analysis, we'll explore symmetric matrices and skew-symmetric matrices. So let's consider a matrix that has all real numbers and m rows and n columns, and let's suppose that we could define this in either two ways. We could say that entry ij of the matrix is the same as entry ji, or this would be by entries, or as matrices with properties, we could say that B is equal to its transpose. And in either case, whether we use entries to define it or we use a matrix equation to define it, we'll call this a symmetric matrix. And it's easy to show that the matrix commutes with its transpose, and that means that such a matrix is a normal matrix. Let's take a very simple example. You can use a spare sheet of paper and we'll erase this when we're done. So let's take an example where B is a 2 by 2 matrix and its first column is 1, 2, and then this entry has to be the same, and then suppose that the other diagonal entry is -2. Well, when I compute the eigenvalues of this using, for example, the characteristic equation, what I get is it has two eigenvalues, of course, and they're distinct, which doesn't always happen. And this would be eigenvalue 1, I compute to be -3, and eigenvalue 2, I compute to be +2. Now, when I compute the eigenvectors, for example, I might take A minus lambda I and find the null space of that. What I find is that V1, which is associated with eigenvalue 1, this is, I'll say, proportional to, that is, it's any scalar multiple of 1 minus 2. And when I do a similar computation for eigenvector 2, what I get is that it is 2, 1. So I have distinct eigenvalues, and here the eigenvectors are not only linearly independent, they're orthogonal, because if I take the dot product, that's 1 times 2 is 2, plus -2 times 1, that's 2 minus 2 is 0. So these are orthogonal vectors. That should be a proportional. And so we can write that, one way that we'll sometimes see it written is that V1 is orthogonal to V2. And that's a property of this particular matrix. A question is, does that happen for all symmetric matrices? Does that happen for all normal matrices? Well, let's erase this and continue. Continuing, there's an important general result, is that if a matrix is symmetric and all real numbers are, and all entries are real numbers. So if B is real and symmetric, then we can make two remarkable statements about it. One is that every eigenvalue is a real number, and a generalization of the property that we observed in a 2 by 2 example is that I'll say if lambda I is not equal to lambda j, that is, if they're numerically distinct, then eigenvector I is orthogonal to eigenvector j. So distinct eigenvalues have orthogonal eigenvectors. In general, if a matrix is diagonalizable, distinct eigenvalues have linearly independent eigenvectors, but now it's a stronger statement. It's that they're orthogonal. So the proof of the real is complex. And I mean that literally, is that to handle that, to prove that it's real, we have to go into complex numbers and then show that it's a special case. Now, we can handle the proof of the second one by expanding something in two ways. So let's try that ourselves. Let's see if we can get this conclusion, right? So let's consider, so I can write, one way to write a multiple of eigenvector I, or let's use 1 and 2. So I could write eigenvector 1, or I could write a multiple of eigenvector 1. And one way I can write that eigenvector multiple is to multiply the eigenvector by that matrix B. And now if I take that and I find its dot product with V2, I can expand this in multiple ways. So that is equivalent to saying, if I expand this, that would be eigenvalue 1 times eigenvector 1, because that's the eigenvalue equation, dot V2. And so that has to equal, that must equal lambda 1 times V1 dot V2. Well, another thing that I could do is I could expand it out as, I could expand V2. So I could also observe that V1, let's say, let's do it this way. Let's say I take B times V1 and I transpose it and multiply it by V2. How can I do that? Well, it's this identity that we'll very frequently use, which is that a dot product can be replaced by a transpose. So what I can do is I can take this vector and I could transpose it and multiply it. So that would equal, so using the rule of transposes, that would equal V1 transpose times B transpose times V2. And you notice here that what I'm doing is I'm taking advantage of associativity of matrix multiplication and getting rid of the bracketing. Well, that has to equal V1 transpose times B times V2. Why can I do that? It's because I'm dealing with a symmetric matrix. So that has to equal, that has to be the same as V1 transpose times, so that would be lambda 2 times V2 when I multiply the matrix B by its second eigenvector, and that has to equal lambda 2, factor that out, and then V1 transpose V2, well, that is That is just v1 dot v2. So now what I'm saying is, if lambda 1, so we're considering the situation in which these are distinct eigenvalues. So lambda 1 not equal to lambda 2, and if we have lambda 1 times v1 dot v2 equals lambda 2 times v1 dot v2, then v1 dot v2 equals 0. And you could conduct this same line of reasoning where if you now replace 1 with I and 2 with J, which I don't do because my handwriting is really bad, right? So if we replace 1 with I and 2 with J, then what we've done is we have demonstrated the truth of this statement. Now, let's consider the third kind of matrix that we began our introduction with, which is a skew-symmetric matrix. So this is a matrix S, and it's all real numbers, and it has m rows and m columns. And this is, we can define it as, in terms of components or entries, as Sij equals minus Sji, or we could define it as S transpose equals minus S, or S equals minus S transpose, etc. And so this is a skew-symmetric matrix, and it's a normal matrix. It commutes with it. The matrix commutes with its transpose, and that's very easy to show. So the eigenvalues of a skew-symmetric matrix are either, so this is a remarkable result, either 0 or they are purely imaginary. So by that 0, so purely imaginary, I mean that that in general the jth eigenvalue equals 0 plus the imaginary number times some value y. And the eigenvalue of a skew-symmetric matrix is either 0 or it's purely imaginary, and then the eigenvectors are generally complex. Each entry of an eigenvector is in general a complex number.